So the topic that we'll be discussing today is mass and weight, and this is the third topic of the first chapter of Igcse physics. First of all, what exactly is mass? If we physically think about when you think about what mass is, what comes to my mind is that how much matter is in an object, how much dense it is, how much heavy it is gonna be. So mass is basically related to the amount of matter in an object. It's written that it is related to, and it is not exactly. You can also write that it is the amount of matter, but it is better to write it is related because density is also a huge factor that tells us about the amount of matter in an object per volume or per size. Now, these two objects, this balloon over here, it seems large, or let's just say if you have a fully blown balloon in front of you, it looks large, but it's not as heavy as this brick. So that basically tells us that how much matter it is in it. Now the second concept, so this is mass. Now the second concept is basically what exactly is weight. Weight, which is denoted by W, is just another word for force of gravity, that is F with a subscript of G. Weight is a force that acts at all times on all objects near Earth. The Earth pulls on all objects with a force of gravity downward towards the center of Earth. The magnitude of the force of gravity can be found by multiplying the mass m of the object by the magnitude of acceleration due to gravity, where g is equal to 9.8 meters per second squared. Now, weight, when sometimes we mix up these terminologies, mass and weight. Like for example, when we go to a fruit vendor, we don't ask him what the mass is of the fruits, or I want 1 kg of um, apples. People don't necessarily say that I want 1 kg mass of apples. They say I want 1 kg weight of apples. However, this usage is wrong in real life. We use it in real life terminologies, but it's not actually scientifically correct. So weight is actually a force that acts on all objects that have mass. Weight acts on masses, and necessarily every object has some mass, minus space or vacuum. So weight is and it's a pull towards the center of the Earth. And because Earth is a sphere, so the center of the Earth is basically downwards, right? Because it should be perpendicular to the center of the Earth. So it points downward if we think about a very small differential area on the Earth. This magnitude is basically 9.81 meters per second square, as it is written here that it is 9.8, but for the simplicity of this course, we are going to use 10 meters per second square. Moving forward, okay, now we are going to discuss some more topics, some more emphasis on what exactly weight is. So we've talked about how weight is defined as the force of gravity of an object and may be calculated by mass times the acceleration. And its SI unit is Newton. Now, for an object in free fall, so the gravity is the only force acting on it, then the expression of weight follows from the Newton's second law. Why do you multiply the mass times the free fall of acceleration when the mass is sitting on the rest of the table? So the question here is that when something is falling from the when something is falling, let's just say from some height, we do see some motion. We can say that it is accelerating. There is a force applied to it. But why do we still even multiply g to every object that has mass, even when it is stationary and it is not moving? So the answer to that is that the value of g allows you to determine the net gravity force. It's not about the motion, it's about the force, and force that is acting on all objects that have some mass. Let it be moving, let it be sitting, or whatever. If so, that is basically the answer to that. And another approach, however, is to consider g to be a measure of intensity of the gravity field in newtons per kg at that location or to that specific mass. Now, this table right here is a very important one, and it's going to differentiate between mass and weight very briefly. So I'm gonna just go over it once. So mass is basically a property of matter, and it it means that the amount of matter that is in an object, the mass of an object remains same everywhere. It is an absolute amount, and it can never be zero, as I told you earlier, and it does not change at location. It is a scalar quantity. It has some magnitude. It has no direction. It's just a property of matter. Mass may be measured using an ordinary balance or using a um, differential balance or whatever. Mass usually is measured in grams or kilograms, and the unit is also kilogram. So this is for mass. However, coming to the other side, weight, however, depends on the effect of gravity, and it is not a singular one absolute number. It can change from on your locations on different altitudes. So weight is basically a force. So it's not a property of matter. It's it's basically the force that the Earth exerts on that specific object, and it can vary. So weight can be zero if no gravity acts upon an object, as in space. Weight increases or decreases with higher or lower gravity. That I also told you earlier, and it depends on basically the altitude. Let's just say if we keep the same planet, if we are talking about Earth, the gravity is different at Antarctica and at India or Pakistan or even in US. So this is where the difference comes. Weight is again a vector quantity. It has magnitude and its direction, where direction is towards the center of the earth, or in daily life what we say is downwards. Weight is measured using a spring balance. Spring balance is basically an instrument which has a scale attached to it, and then you hang the weight to it or an object to it, and it gives you the force that is applied to it. Weight often is measured in newtons or newton to force. W is equal to mg. That is the formula that you use to find out the weight, where m is the mass and g is the gravitational acceleration that in this course you are going to take as 10 meters per second squared. The unit is Newton, but if you write it in base units, then it can also be written as m, which gives you kg, and g, which is acceleration, so that gives you meters per second squared. So the units of weight are basically kg meters per second squared. Moving forward, this is the formula that you need to keep in your head and you need to memorize it. It's not very difficult. Again, that says that weight is a force, it is an external force, and it applies at all times, even if an object is not accelerating. Let it be hanging, let it be sitting on a table, let it whatever. If an object has the mass, it has to have experienced some weight. It experiences the force of gravity that we call weight. If the object is in free fall with no other force other than gravity, then its weight is equal to the force that is acting upon it. We are going to discuss in later chapters how um, this can get different when an object is in free fall and there is some consideration for air resistance or other forces. But till we don't consider it, you need to know that when an object is in free fall, the force acting on it is also weight. That the force that is pulling it downwards, that the reason that why it's coming downward, why it's accelerating downwards is that force. So these are some measuring and comparing weights, and that's just the topic. This basically shows some instruments that are used to measure weight. Now, the first one is a mass balance, and in this basically we compare two masses. So you can see there are 5 to 6 of these weights that are lying on the table. Sorry. So if you put, let's just say, they have their calibration on it. One of them has 1 kg, other one would have 2 kg, 3 kg, 4 kg, or whatever. They can be, of different set weights. So if you put one of them on one pan, then and if you put something on the other pan, then you can take an idea of, if the object that you're measuring is heavier than your um, the weight that you put there. Let's just say if it balances out exactly at the scale is horizontal exactly at 1 kg or 2 kg or whatever that is, then we know that this is the weight. Well, this is kind of erroneous, and it does produce some errors, so it is better to use something that has absolute scale in it. One of them is digital weight scale. Digital weight scale is a very precise and accurate scale in which it gives you the weight of the object or the mass of the object, however it is calibrated, in simple numbers. Like there is a small screen on it, and the screen on it, and it shows the direct weight of the object. However, the last one is that of spring balance, and spring balance is basically a balance which you hang somewhere, and then there is this little hook over here. Wait, this hook over here that you can use to hang stuff. Let's just say I have to measure this ball, so I'll hang it here, and then I'll also, vertically hang this thing from somewhere. And then this scale over here will mark somewhere, let's just say here or here. So it will show us the reading of what is the reading or what is the weight of the object. Spring balance basically shows the weight of the object. Moving forward, mass is a measure of inertia. Now, we are going to talk about the concept of inertia, that what exactly is inertia. Before that, there is a need to know that all objects resist changes in their state of motion. If you think about it, um, let's just say you are going somewhere on your car and you want to stop. So there is some brake that you need to apply. The first case that I told you about in which the car was moving and you had to apply brake was the case when an object is in motion, and and the change in motion is to basically stop it. Let's say the other way around. Let's just say if an object is stationary and you have to move it and you want it to move, then again there is some force that needs to be applied. So again, this the concept is that all objects resist changes in motion, that they need some force or they don't move on their own. So all objects have this tendency, they have inertia. The tendency to resist change in their motion is basically called inertia, and it is a measure of, and mass is basically a measure of inertia. By that, it basically means that mass is directly proportional to inertia. That if an object has higher mass, then it's more likely that it would be very difficult for it to move, or more force would be needed to make it move. But do but do some objects have more tendency to resist changes than the others? Absolutely yes. The tendency of an object to resist changes in its state of motion varies with mass. Mass is a quantity that is solely dependent upon the inertia of an object. The more inertia that an object has, the more mass that it has. A more massive object that has greater tendency to resist changes in its state of motion. Well, again, it is. Let's just say, yeah. Let's just take a very simple example. Let's just say you were dragging some books of yours or some objects or some things of yours on a trolley. If you have one book on it, it would be you would still need to apply some force or some um, you would have to give it a push to make it move, right? To put it in a position where it is moving or going, right? So, however, let's just say instead of one book, if you don't put 10 books on it, we know that we've increased the mass. Hence, there is need of more force or more application of push to make it move. So 10 books have higher inertia, and because they have more mass, hence they resist changes in motion more, and they want more push or more force to make it move. This slide was topic was very small compared to the last